So today we are going to start on this exciting adventure that we call beam design. And so the very first step is that we need to learn about bending stress. So we're going to go ahead and look at the basics of bending stress. So the first thing is we need to look at how a beam deforms when it's bent. So if we have a beam and we apply a moment about an axis that is perpendicular to an axis of symmetry, so that's a very important limitation of this class, is that we're choosing an axis that is perpendicular to an axis of symmetry. So for example, this z-axis is an axis, it's perpendicular to an axis of symmetry. This particular figure, I think, is symmetric in two directions. But anyway, then we're applying a moment about that axis. So we're applying a moment that causes the beam to deflect into a arc shape, like you see here. So those two moments on either side cause it to deflect into a curved shape. So when we do that, the length of the longitudinal axis within what we call the neutral surface remains unchanged. So you remember that there's a centroid. You can calculate the centroid of a cross section. Cool. If it's a rectangle or a circle, it's going to be at the center. If it's something like a T, then you have to actually calculate. So the neutral surface passes through that centroid. And so here, the neutral surface is given by this orange surface. And as this bends, that surface remains the same length. It doesn't change. But what happens is that the portions of the member that are above get shorter, the portions that are below get longer if it's bending so that it's concave up. If it's bending so that it's concave down, of course it's the opposite. Now I have shortening below the neutral axis and extension above the neutral axis. When we do this, what do you notice about cross sections that were initially perpendicular to the longitudinal axis? So we have our longitudinal axis, we have these cross sections that are initially perpendicular. What do you notice about them when it curves? They're still perpendicular to the longitudinal or the neutral axis, right? So, so all of these lines here that were initially perpendicular to that longitudinal axis, when the longitudinal axis curves, they're still perpendicular to it. They're just kind of curving in. We're going to neglect the Poisson effect. Technically speaking, it occurs. So you see that this is our neutral axis. See how it's kind of getting wider up at the top and more narrow at the bottom? That's that Poisson effect. But we're going to neglect that and just, in this class, presume that the cross sections stay in their normal cross-section shape, with the exception that they're elongating and contracting. Okay, so these material lines that are parallel to the longitudinal axis are going to deflect into arcs of a circle. So what that means is if we have this member and we have, say, the neutral surface, we'll call that neutral surface AB. And then let's say we have another line, CD, that is located some arbitrary distance y away from the neutral surface. When this bends due to pure moment, so we apply a moment to either end. AB has the same distance, but now CD is going to span a shorter distance, and we'll call these C prime, D prime, A prime, B prime. And you can see that this is creating a circular, this is a portion of a circle, right? So if we draw those lines, it's going to come back to some center of that circle. Now the measurement to our neutral surface is rho, and the measurement to C prime, D prime is then rho minus y. And initially, the distance AB is equal to the distance CD. And on the neutral surface, we know that AB is also equal to A prime, B prime, because one of our kinematic assumptions is that it doesn't extend or contract. We know that when this creates a section of a circle, A prime, B prime is going to equal rho times theta. Is that correct? That arc length is the radius times theta, where theta would be this value. And C prime, D prime is going to equal rho minus y times theta. Cool. All right, so let's look at our axial strain. C prime, D prime minus CD gives us our change in length, and then we divide that by CD. Would you agree that that gives us the axial strain in member or in line CD? Okay, so then we know that C prime, D prime is rho minus y times theta. CD, we don't know that value, but we know it's equal to AB. And we know that AB is equal to A prime, B prime, which we know is equal to rho theta. Did everybody follow that? Let me give you some helpful arrows. We're looking for CD, which is equal to AB. AB is equal to A prime, B prime. A prime, B prime is equal to P theta. Therefore, I can say that CD is equal to P theta. This all then gets divided by CD, which is rho theta. So you can probably imagine that those thetas get removed from the picture. And what are we left with? Negative y over rho, right? So strain is equal to negative y over rho. Does everybody see that?
Yeah, so for CD, it's rho times theta, because it equals AB. But isn't AB equal to CD or no?
In the initial configuration it was,
Oh, right.
but not after it bends.
So C prime, D prime is not equal to CD.
Correct.
Only A prime, B prime.
Only the neutral surface stays the same. Everything else changes.
So then if CD was on the other side of AB, would you have to flip this side?
No, but you do bring up a very good point. Our y is measured from the neutral surface, and it's positive when you go upwards, and it's negative when you go downwards. So you don't the formula would end up being the same, but you would plug in a negative value of y, and so then it would end up being an opposite sign. It'd be a positive value. Good. Okay. So here's our takeaway. The strain, I'm saying that the longitudinal direction is the x direction, so that's why I have that x subscript. It's negative y over rho. Shortening occurs above the neutral surface, extension occurs below, and this finding is specific to a positive moment. So it's specific to when our moments are like that. Otherwise, you have the opposite. Okay, you remember generalized Hooke's law?
Sigma x over v
Okay.
minus sigma x over mu. No, not sigma x. Sorry. No over e. Yes, times sigma y minus sigma.
Good. Does everybody agree with that? Looks good. Okay, so no, because we're solving for strain. Okay. So in this type of loading, bending, we have normal stress in the longitudinal direction, and we presume that the other two stresses are zero. It's an assumption that is very close to the reality. And so therefore, these two are zero. So we're just going to use the simplified version. So what that says is that the stress in the x direction is the strain times E, which is equal to negative YE over rho. Okay, so now we have an equation for our stress. Now notice that both our stress and our strain are linear functions of y. So what that means is that our strain and our stress, if this is our cross section, in both cases, they look like this, right? Or this is, I feel like I probably drew that backwards. You typically put your compression the other way, right? There we go. Well, either way, one side is compression, the other side is tension. And actually, that only makes sense for stress. But for the strain, we have contraction and then elongation on the bottom. And it's going to be a linear variation. And right here, where it passes through zero, that's going to be your neutral surface. Yes?
Kind of like don't understand.
So if this were our beam, what I'm saying is that this represents a plane on that beam. And I'm saying that the strain at any point is given by that curve or that line. So if you wanted to know the strain at the top, it would be this negative y over rho value. At the bottom, it'd be negative y over rho, and then it would linearly vary in between. And same thing for stress, except it now is negative EY over rho. Sure. Okay, so now we have force equilibrium. On the cross section, it has to be in force equilibrium, which means when we have that distribution of stress, if we were to integrate it, it needs to integrate to equal 0. So the compressive stresses are offsetting those tensile stresses so that they equal 0. So we want to take this come back here. Oh. We want to take the sum over the area of sigma x dA, where sigma x is equal to negative ye over rho. Okay. We can pull e and rho out because those are constants. And we can pull the negative sign out. And what's left is the integral of y dA. And we know that that has to sum to equal 0, right? Can e over rho ever equal 0? No, those are constants, they can't equal 0. Which means that this integral must equal 0. Those of you who have been in statics recently, does this look familiar? No? When you talked about centroids, did you see this integral? Yes. Right, so this is basically the definition of your centroid. Your centroid is placed so that when you integrate y with respect to area, so you break your shape up into little areas and you do the calculation of the distance from the centroid to that area multiplied by the area, you sum all those up, it has to equal 0 if that truly was your centroid. That's how you place your centroid, is by taking the sum of distances to areas. All right, so therefore what force equilibrium tells us is that our neutral section must pass through that centroid. Because we're measuring y with respect to our neutral section, we now know that that is at the centroidal location. So the other thing we can do from statics is take moment equilibrium. Only slightly more difficult, only slightly. So let's look at our cross section. So now we have these little material elements. Each one has a stress acting on it. And when we multiply that, or let's see, if we integrate just the stress, we get a force, right? Stress integrated over area is force. But we want moment. So that force needs to be multiplied by the y, by the distance to the neutral axis. Okay, so we're going to integrate over the area the distance y times the stress integrated with respect to area. Now, when we have see if I can explain this properly. this is going to equal our applied moment, okay? So let's say we have this moment, remember, that was putting it into a positive bending moment. And that's going to give us compression on the top, tension on the bottom. This is going to be a positive stress on the top. And it's going to be multiplied, or I'm sorry, negative stress on the top. All right, we're gonna have a negative sigma x on the top, and it's going to be multiplied by a positive y value. So that's going to give you a negative moment. But that's not what we want, right? That compression is coming from a positive moment. So we need to sneak in this little negative sign. The sole purpose of that negative sign is to get the two different sign conventions to work together. The sign convention for what we call positive and negative moment, and the sign convention for what we call positive and negative stress. Right? So this negative sign makes everything work nicely. Okay, so we are integrating negative y times, this is negative ye over rho dA has to equal the applied moment. And let's see, I'm going to pull out a negative e over rho. So I'm just going to be integrating y squared dA. So now, who is this friendly character? Oh, because I forgot that two negatives make a positive. Integral of y squared dA.
So the other one was the centroid.
Right? So what kind of goes along with the centroid? Yeah, little less concretely. What sort of goes along with a centroid? You learned about centroids and then you learned about... Oh, you're killing me. Co-requisite. You need a co-requisite. No. Moment of inertia? I? All right. There's this thing called I. It's the moment of inertia, and you get it by integrating y squared dA. Yeah. And like for rectangles, if I have a rectangular cross section, it's 1/12 BH cubed. Do you remember that? Okay, well that's the I. Okay. For a rectangle. Okay. All right, so the really cool thing about this is now we have this equation that says EI over rho equals M. And I didn't leave room for it, but there's an important statement. So EI over rho equals M. This is our moment curvature relationship. This is the material relation for bending. So you know how we had the force deflection, and then we had the torque twist? Well, now we have moment curvature. And it's how the moment M relates to the curvature rho. Or 1 over rho is really curvature. Rho is the radius of curvature. So here's the two equations that we have so far. We just got the, well, I flipped it around, didn't I? Let me see. We had M equals EI over rho. So now I switched the location of rho and M. Totally fine. And previously we had that the stress is negative EY over rho. I don't really like rho, right? If you like it, it's fine. But I don't really like rho. I don't want it in my equation. So I'm going to get rid of it. Let's say stress equals negative EY over. For rho, I'm going to plug in EI over M. So stress is now equal to negative, well, my over I. Sometimes referred to as the most narcissistic equation in this class. Most narcissistic.
Oh, okay.
Right. Negative my over I. I didn't make that up, but it's good. So now we have an equation for stress that doesn't have rho in it, because we don't really know rho. I don't bend a beam and say, oh yeah, that sure looks like a radius of curvature. You don't do that. But what you do know is how much moment was applied. So now, knowing the cross-sectional properties, y is a cross-sectional property, right? Y could be the vertical location of a bending beam really to any point on that beam. But if you want the maximum value, it's from the neutral axis all the way to the end. I is based on the cross-section. If it's rectangular, that's 1/12 BH cubed. If it's not rectangular, there are other formulas. Or if you can make it out of other small rectangles, so if you can make it out of two rectangles, each of those is 1/12 BH cubed, and then you have the parallel axis theorem, which is where you add AD squared, where D is the distance that you need in order to move it from the centroid of its shape, like the centroid of that flange, to the centroid of the whole thing. So that would be your D. All right, so those two are from geometry. Moment comes from statics. You can get moment from your moment diagram. Put it into this equation, bada bing, bada boom, you got stress. Right? And you'll notice that it is not a constant stress. It's varying with y. So if you have a beam, it's going to depend on where it is in that. So there's your cross section. Wherever you are in that beam, you're going to get a different value of bending stress. So if I take this little square versus that little square versus that little square, I'm going to get different values because the moment is changing along the length, assuming that it's not a constant moment. So in today's lecture, everything was constant moment. So in that case, that's no longer really relevant. But when you get to the real world, we'll have other loading scenarios that aren't constant moment. Your moment will be changing in this direction. Your y is changing in that direction. So really anywhere on this beam, you're going to get a different value of bending stress. And, oh yeah, and then to balance the load. So what I mean by balance the load is if you want to have this member reach its bending stress capacity in tension at the same time that it does in compression, you need to make it so that you need to design it so that you reach this value for both the positive and the negative bending stress at the same time. So that might mean like you have to move one of your supports around so that you balance the moments so that you reach the same stress at the same time. So that's one thing that we can do in this class. The reason it's important is so that you don't have something that's like way over designed in tension, but then is going to fail real quickly in compression. It's just to kind of make it so that you're cost effective with your design. But it really is going to depend, and those capacities may be the same value, may not be the same value. Really what's most important is just that you foresee all of the different ways it could fail. So you say, oh, it could fail in compressive stress, it could fail in tensile stress. I want to make sure it's strong enough in both of those regards. And then when you're talking about balancing, that's more of like a cost effectiveness, trying to make sure you're not like over designing in one way. Did you have another question? Yeah. Cool. All right, a brief example and then we'll be done. Determine the maximum tensile and compressive bending stress. Okay, so the equation we want to use is negative my over I why don't you start by figuring out how to calculate I. So this is not a rectangle, so it means you might need to do a little research. Figure out how to calculate I, and I will track down the magnitude of this moment. Okay, so the moment that we're going to use is 800 pound-feet. Did anybody get an equation for I? Yeah, that sounds more familiar. I'm not sure what that other equation is, but I should be 1/36 base times height, right?
Yeah, sure.
Okay. All right, so 1/36. The base here is 4 inches. What is the height?
Root 5.
So you said square root 5?
2 root 5.
2 root 5. Can I say square root of 4 squared minus 2 squared? Is that the same thing? Okay. So in the end, I believe you get 4.62 inches for I. No, that inches is not right. Inches to the 4th. Is that what you have? All right. So now which side is going to be tension? The top or the bottom? Bottom is tension, top is compression. Good. So if we're going to do our maximum tensile stress, we want to use Y going this direction. So the height, this height here, square root 4 squared minus 2 squared, that simplifies to 3.46 inches. This distance, Y, to the bottom is going to be 1/3 of that, correct? Okay. So for tensile, stress is going to be negative 800 pound-feet. Y is a negative value because we're measuring it downward. And it is 1/3 of 3.46 inches. And then divided by 4.62 inches to the 4th. And that should give us a negative 4.8. Oh, no. Negative and negative is a positive. And it's not 4.8. Excuse me. It's 2.4 KSI. But that number is correct, but there's a unit conversion problem in here. So I have pound-feet and I multiplied it by inches. This here needs to have 12 inches per feet. So there's that 12 is included in that 2.4 calculation. Okay, so that is our tensile, our compression. Is negative 800. Now it's a positive, well, let's multiply it by 12 before we forget. Now it's a positive Y, and it's multiplied by 2/3. That's the distance to the top of the triangle. So 2/3 of 3.46 inches. And then we divide by 4.62 inches to the 4th. No, yep, I stays the same. I never changes. That gives us a negative 4.8 KSI. So those would be your two stresses at the 2.4 would be at the bottom. So 2.4 KSI in tension is at the bottom, negative 4.8 KSI, that's compression, would be at the top, and then it would be linear in between there. And at this centroidal level, or the neutral surface, it would be 0. Cool beans? All right, let's go.